Hi everyone. In this video I want to talk about the concept of word vectors or word embeddings. This is an important concept in natural language processing, and it's also sometimes used in search engines. The basic problem we want to tackle is how to identify words that are quote-unquote similar in meaning. Similarity in this case is not limited to synonyms, but more generally refers to words that have a common context. For example, the word cat and the word dog are not synonyms, but they are linked through a common context, which is pets. To quantify how similar two words are, we need to encode them in some sort of numerical form. We can do this by associating a vector with each word, such that words that are similar in meaning have similar vectors. These are called word vectors or word embeddings. This brings up a couple of questions. First, how do we generate these word vectors in the first place? And second, how can we measure similarity between vectors and therefore similarity between the words they're associated with? The answer to the first question is a bit technical, so I'm going to avoid that discussion for now and just say that these vectors can be obtained by training a model on a large body of documents, and that, for example, words that occur frequently close together in the training documents will tend to have similar vectors. So for the second question, how can we tell if two vectors are similar? One way, and it's not the only way, is to look at the angle between the vectors. The smaller the angle between the vectors, the more similar they are. The larger the angle, the less similar they are. And so, therefore, if we find two vectors that have a small angle between them, we can sort of surmise that the words are similar in meaning. So let's look at a concrete example using Python. So for this, you'll need to install the gensim package, which you should be able to do at any command prompt using the usual pip install command. And what we're going to do is we're going to use the gensim downloader to fetch a file that contains words and their associated word vectors. So the first time you run this command, it'll actually fetch the file from the web and download it, but after that it shouldn't need to. So let's start by taking a look at this particular file. The word glove here refers to global vector, which is the name of a particular model used to generate the word vectors or word embeddings. And this particular model was trained on data from Wikipedia and GigaWord databases. And this 200 number here refers to the size or the dimension of the vectors. And we'll see that a little later on. We can get some information about the contents of the model by using the info method, like so. So now let's look at the words that actually make up the vocabulary of the model. And we can start by getting the number of words that are included. And so we have 400,000 words in the vocabulary. But not all of these words are necessarily interesting. So let's take a closer look. And you can see that some of the words are actually punctuation marks, which is not something we necessarily want to work with. So let's first make sure that we're only dealing with words that are composed of letters. And you can see that takes care of the punctuation marks. Let's also look at how many words we have left in this list. You can see that there's fewer words now, but it's still quite a large number, 327,000 or so. Now, remember that the point of this whole exercise is to compare words. So let's look at how much information we need to store to do that. First, suppose we use a naive approach, which consists in making all possible pairs of words in the vocabulary and assigning a numerical similarity score to each pair. Never mind how we do that. Let's just worry about the storage issue for now. So to do that, in this naive approach, we would need 327,091 times 327,090 divided by 2. Or about 53 billion. That's billion with a B. Now the way I got this formula is I took the number of words, which is the number of choices you have for the first word in the pair, times the number of choices for the second word in the pair, assuming that I'm not interested in comparing a word to itself, and then divided by 2 because the ordering of the words doesn't matter in the pair. Now let's compare this with the storage we need if we use the word vectors that are in the model. And for this, all we need to store are the 327,000 words multiplied by the size of each vector, which is 200. And this is a considerably smaller number that we need to deal with. Now let's compare some words. Let's look at the vector for the word cat, for example. And we can get that this way. So you can see it's just an array of numbers, and we can verify that the length of this array, or of this vector, is 200 as advertised. And it is. So next, let's store this vector and normalize it so that its length is equal to 1. And we'll use the NumPy library to do this. Notice that we had to get a copy of the word vector so that we could modify it when we normalize it. If you don't have this, then you will get an error message, and you'll know what that's due to. Now let's do the same for a few other words. Let's do this for the word dog, for example, and we'll store it in a different vector. And for the word car, for example. So now we can compare the vectors for these words. Now, earlier I mentioned that one way to compare two vectors is to measure the angle between them. Mathematically, we can do this by taking the dot product of the vectors. Since we've taken the trouble to normalize these vectors, their dot product will simply be the cosine of the angle between them. The closer that cosine is to 1, the smaller the angle, and the more similar the words, the vectors and therefore the words will be. So for example, let's compare the vectors for the words cat and dog using the dot product function in NumPy. And you see that we get a number that's fairly close to 1. We can do the same for the vectors that correspond to cat and car, for example. And there we find something that's not as close to 1 as expected. And the same goes if you compare dog and car. And again, it's a number that's pretty far from 1 compared to the number we got when comparing the vectors for cat and dog. So finally, the model provides a similarity method which allows you to compare the vocabulary words directly without having to first extract the vectors. So let's try that. And you see that this is pretty much the same number we got by taking the dot product of the vectors. So that's how it's done internally. And that's it for now. Bye.